One of the more familiar applications of lasers is in holography, which is a process for producing three-dimensional images. The information used to produce a holographic image is captured on photographic film, which is referred to as a hologram. Holograms often appear on currency and credit cards as a security feature. Here we illustrate how a hologram is made. Suppose we want to make a holographic image from a three-dimensional object such as this chess piece, in this case a rook. Looking from the top, a beam splitter, which is a half-silvered mirror, and a photographic film are set up as seen here. Laser light strikes the beam splitter, which reflects part and transmits part of the light. The reflected part is called the object beam because it illuminates the object. The transmitted part is called the reference beam and goes directly to the film. In order to analyze what is happening, we can look at two parts of the incoming beam. The object beam reflects from the chess piece at points such as A and B, and together with the reference beam, falls on the film. One of the main characteristics of laser light is that it is coherent. Thus, the light from the two beams has a stable phase relationship, like the light from the two slits in Young's double slit experiment. Because of the stable phase relationship, and because the two beams travel different distances, an interference pattern is formed on the film. This pattern is the hologram, and, although much more complex, is analogous to the pattern of bright and dark fringes formed in the double slit experiment. To explore in greater detail how a holographic interference pattern arises, we consider only the reference beam and the light of wavelength lambda coming from point A on the chess piece. As we know from section 27.1, constructive interference between two light waves leads to a bright fringe. It occurs when the waves, in reaching the film, travel distances that differ by an integer number m of wavelengths. In the drawing, Lm is the distance between point A and the place on the film where the mth order bright fringe occurs, and L0 is the perpendicular distance that the reference beam would travel from point A to the m equals 0 bright fringe. In addition, Rm is the distance along the film that locates the bright fringe. In terms of these distances, we know that the condition for constructive interference is Lm minus L0 equals m lambda, which we can solve for Lm as Lm equals m lambda plus L0. Next, we see that Lm, L0, and Rm form a right triangle, and using Pythagorean's theorem, we write L0 squared plus Rm squared equals Lm squared. We can now substitute for Lm and rearrange to give Rm squared equals m lambda times m lambda plus 2L0. The reason we write it this way is that we can take advantage of the fact that 2L0 is much greater than m lambda. For instance, L0 is usually around 10 to the minus 1 meters and lambda is around 10 to the minus 6 meters. Therefore, we can eliminate the m lambda term in the brackets and find that Rm is approximately equal to the square root of m lambda times 2L0. Or we can say that Rm is roughly proportional to the square root of m. This means that the fringes are more spread out at the top of the film, near where the central maximum would be located, and closer together near the bottom, where the higher order fringes occur. For example, the distance between the m equal 1 and m equal 2 fringes is proportional to square root of 2 minus the square root of 1, which equals 0.41, whereas the distance between the m equal 3 and m equal 2 fringes is proportional to the square root of 3 minus the square root of 2, which is smaller at 0.32. The total interference pattern on the hologram includes interference effects that are related to light coming from point B and all other locations on the object. The total pattern is very complicated because it is the overlapping sum of the diffraction patterns from every point on the object. The question now is, how do we view the hologram once the holographic film is created? The fringe pattern for point A is sufficient to illustrate the fact that a hologram can be used to produce both a virtual and a real image of the object. Consider 2 points on the holographic film produced by light reflected from point A. At the position of the upper point, there is a wider fringe spacing, and at the lower point, there is a narrower fringe spacing. To produce the holographic images, laser light is directed through the interference pattern on the film. The pattern can be thought of as a kind of diffraction grating, with the fringes analogous to the spaces between the slits of the grating. For each point on the film, we show 3 rays that correspond to the central and first order bright fringes. The angle theta, which locates the first order fringes relative to the central fringe, is given by the grating equation, which is equation 27.7, with m equals 1, as sine theta equals lambda over d, where d is the separation between lines of the grating. When the slit separation is greater, as it is near the top of the film, the angle is smaller. When the slit separation is smaller, as it is near the bottom, the angle is larger. Thus, we have drawn theta top smaller than theta bottom. Of the 3 rays emerging from the film at the top and the 3 at the bottom, we use the uppermost one in each case to locate the real image of point A on the chess piece. The real image is located where these 2 rays intersect when extended to the right, as seen here. To locate the virtual image, we use the lower ray in each of the 3 ray bundles at the top and bottom of the film. When projected to the left, these rays appear to be originating from the spot where the projections intersect, that is, from the virtual image. A holographic image differs greatly from a photographic image. The most obvious difference is that the hologram provides a 3-dimensional image, whereas photographs are 2-dimensional. The 3-dimensional nature of the holographic image is inherent in the interference pattern formed on the film. This pattern arises because the light emitted by point A travels different distances in reaching different spots on the film than does the light in the reference beam. The same can be said about the light emitted from point B and every other point. As a result, the total interference pattern contains information about how much farther from the film the various points in the object are, and because of this information, holographic images are 3-dimensional. Furthermore, it is possible to walk around a holographic image and view it from different angles, as you would the original object. A vast difference exists between the methods used to produce holograms and photographs. A camera uses a converging lens to produce a photograph. The lens focuses the light rays originating from a point on the object to a corresponding point on the film. To produce a hologram, lenses are not used in this way, and a point on the object does not correspond to a single point on the film. For instance, light from point A, as shown here, diverges on its way to the film, and there is no lens to make it converge to a single corresponding point. The light falls over the entire exposed region of the film and contributes everywhere to the interference pattern that is formed. Thus, a hologram may be cut into smaller pieces, and each piece will contain some information about the light originating from point A. The same is true for point B and all other points. For this reason, each smaller piece can be used to produce a 3-dimensional image of the object. In contrast, it is not possible to reconstruct the entire image in a photograph from only a small piece of the original film. The holograms discussed here are typically viewed with the aid of the laser light used to produce them. There are also other kinds of holograms. Credit cards, for example, use holograms for security purposes. This kind of hologram is called a rainbow hologram and is designed to be viewed in white light that is reflected from it. Other applications of holography include heads-up displays for instrument panels in high-performance fighter planes, laser scanners at checkout counters, computerized data storage and retrieval systems, and methods for high-precision biomedical measurements.